So a wonderful voice that woman has, telling us it's recorded. So I'll start off with just a little uh, a, a summary of what the talk is about, so that if people don't want to listen to it, they can go. Right. So I've bored people senseless by talking about elicitation in terms of structural elicitation, and there was a great conference in Delft about 4 or 5 years ago, I seem to remember, where I was talking about this stuff. And I was arguing that you should use bespoke graphs. Think not just about Bayes nets, but other sorts of graphs that actually link in to the sorts of structures that you're talking about. Because in terms of, if you can get some sort of formal way of actually expressing that graph so that it can translate ideas into probability distributions and processes more or less directly, then the elicitation process becomes a lot easier, because people just tell you about certain things, and then it becomes about parts of that graph. One of the things that I've been working on over the last 20 years or so is causation. And what often you find is that graphs have a sort of causal interpretation. And by this, I mean that the graph doesn't just describe a structure on a data set, but in some senses it describes the underlying processes driving what's going on. And in fact, when we do elicitation, this is the sort of thing that we should really be focusing on anyway, not just how the data is structured. So the idea of causality and the way and decision analysis and the way that we draw graphs and things are all linked together. And the basic idea is, with causation, is that a particular structure is so generic to a domain that it continues to apply even when you make interventions or decisions. The actual structure of the process, as described by the graph, remains invariant, right? And furthermore, another idea of causation is that when you talk causally about how things happen, the causal explanation is a sort of credible explanation to other intelligent people as well. This is something which is often lost by the machine learners, but right back in the 60s, where there was this guy called Bradford Hills, a British statistician who was doing lots of stuff that was translating what Fisher was doing. And this was one of his big things, that when you're talking about causation, it should have something associated with it being something that's an acceptable way of expressing how things actually happen. Right. And I've been looking at these adversarial types of settings where we've got people trying to do nasty things. And very often these are states or organized by states. And one of the things that's coming out here is that if a defender believes a graphical model is causal, then other intelligent people will believe it's causal too. And therefore, it's not implausible to assume that the adversary has the same sort of causal explanation as the defender, right? So in this sense, the jump is to say, well, that graph also expresses what this other person is doing, right? And when we set this against some work that is led by a guy called David Rios Insua, who we all probably know pretty well, and I met him as a postdoc of Simon French's, actually. But he and David Banks and Navarra have worked together this idea of adversarial risk analysis, which is a Bayesian probabilistic way of treating game theory that allows you to actually structure things in a sensible way, which I'll talk a little bit about later. But if you start looking at this in the context of graphs, a causation, then it becomes not only a really fascinating way of looking at games, but also makes it possible to elicit the sorts of structures of games that you might want to do, right? And I'll show you how this works. There, you can't just do ordinary graphical models. You have to bring in some latent variables, knowledge, intent, and capabilities before of the adversary, as you typically have to do in any adversarial sense. But if you build that into the graphical framework as latent variables, then you can start being able to double guess what your adversary is going to be doing, through looking at the graph, assuming that it's representing how things happen, right? And this is a co-creation. This stuff I'm talking about here is I've been doing for about 10 years now, and we've got lots of examples. I will work with a very simple illustration to give you the basic flavor of this thing, so you just get the idea. There is now a paper that's that supports this, which I've had sanitized by my friends, and this is essentially a digest of this. It's a paper on arXiv, and it's listed second on the list of references here. So if you want to read up more about the technical stuff associated with that, you'll find it there. It's just we wrote it 6 months ago, and we got the approval a couple of weeks ago to actually put it on arXiv, so submit it. So that's where it is. So a little while ago we were talking about bespoke families of graphs and saying those are good, and we're saying that they should be causal. So I'll start talking about causation in terms of general graphs, right? And I'll illustrate a couple of these things, and then we'll look at adversarial risk analysis and start talking about intelligent causal algebras, where you use these frameworks to try and discover, to try and work out how the defender will react to things if they discover what you're doing, right? So and then there's a silly example, and I'll show you, and then I'll go on to what's going on. Right, so these are my basic assumptions. I'm going to start by assuming that you've got a defender. They're always D. They're intervening with a decision D in a black ball D, and they're going to be trying to do things, and I'm going to let D sub phi represent doing nothing. And I'm going to assume that both the defender and the adversary are going to be intelligent and rational. And of course, being a card-carrying Bayesian, that means to say I'm going to assume both are maximizing their subjective utility. This stuff generalizes away from that, but that makes this a lot easier just to keep to doing that, right? So that's what I'll be doing. And the xi is just the variables in the system. And we have a density or a probability mass function over that. And the idle system is always what happens if you don't intervene or try and control the system with a significant decision. And of course, if you assume this, then both the defender and the adversary will try and maximize their expected utility scores, which I've given there, given the probability distribution that they get from what they do, which is that P sub D E, where E are the effects or the attributes of the utility function, right? And so the question is here, if we can, if the decision maker can specify their probability distribution, then they can work out these scores, right? So the question is, how do I do that for lots of Ds? And if I've got a graphical model that can express this thing for the usual thing, and then I can sort of say it's causal, then the graph carries how I actually write this sort of thing. So let me show you how that works. Right. So the first point that I want to make is that the causal graph, if it's truly causal, can be used to frame this probability density that you're going to get associated with any decisions. And also what tends to happen is, because this is a process and because an intervention tends to act on some part of the process and then lets everything go, right, then most of those probability factors will remain invariant. And it's only one or two that you have to change. And this means that, you know, you've got this set of variables that you're interested in, you extend them. You've got an observed system which you can then learn about using some sort of data analysis or whatever. And then you can get your probability distributions associated with the decisions simply using the graph and saying that my estimates associated with some of the factors associated with this probability distribution will stay the same, most of them, and a few will change. And then I produce my forecast, right? So doing this means to say I create something called a causal algebra, right? And the point of, in terms of the elicitation here, is that the elicitation then becomes orders of magnitude smaller, because what we have, we can elicit the stuff associated with the idle system, and then just a few things for the few probabilities associated with the intervention, and then you can calculate the things you need to calculate, right? So this is just a bit of maths here, but so this is just saying mathematically what I've just said, right? So, but it's there if you want to look at it. So this graph, if it's chosen properly, has sort of 4 rules. The first thing that if anybody does elicitation, you tend to start by saying, well, tell us about this, what's going on. And, and I tend to draw pictures and things and what's going on. So a good graphical model is something that represents sort of natural language explanations that are being given to you, right? And if we craft these well and we match this to the logic of probability models, this can be translated then into some sort of family of probability models, right? And what we need to do is just take that graph and then paste in these probability factors, and then have a formula that will then give us the joint distribution across this big vector xi. And then that gives you marginalize that and you get the probability distributions that you need, right? And what we're hoping for here is that this G has 4 things. It allows a conduit for this natural language explanation. It automatically gives meaning to the factors. It also, the meaning of the graph gives you the way in which you combine those different factors together, right? And most of those factors, because it's causal, most of those factors will stay the same. Only a few, the things in this curly P1 G will differ.
Can I ask a quick clarification? Are these directed graphs?
They can be anything.
They can be anything.
Yes.
And this distribution over the invariant part, is that the same for the adversary and the defender?
I'm assuming that the graph is yes, that because it's deemed causal. This is a description of how certain things happen, certain crimes happen, for example, right? That graph would be shared if you did the thing with did an elicitation with the adversary, right? Okay. Just the broad out. Okay. Now, the semantics of it all will stay the same, but the bits of it, the probability judgments and things, of course, may change a lot, right, between the different people. They may know different things, for example, but the actual structure stays the same.
So, but I mean, my question was this distribution P over the invariant parts of the graph, that's shared, or is that different for the defender?
It will be different both for the defender when they consider doing different things, and for the adversary who will know certain things that the defender won't know.
So the defender has to think about what the adversary believes.
Yeah, absolutely. Absolutely. Okay. So the basic structure is the same, but you still have to do this almost infinite regressive thing. But the nice thing, Roger, is that you're thinking only about small parts of the problem rather than the whole composite, right? So that's what you save.
Mm-hmm.
So an example you said with is this a directed graph? Well, it could be, right? So it could be a DAG, it could be a Bayes net, or call it a Bayes net, right? And here what you have, the natural language statements of conditional independence statements associated with what you use one thing, what you can use to forecast another thing, right? So that's what this means. And then when you've got that structure, which you've represented by a graph, like the one below, this gives you a formula which takes certain factors, which are the conditional probability tables, and then just multiplies those together, right? So we have this thing that is you elicit from natural language statements, and then you embellish by you doing probabilistic elicitation into a full model, right? So we do that all the time when we're looking at Bayes nets, right? And then if you're looking at a Bayes net here, then you can think when you say a Bayes net is causal, what you typically mean is that when you take certain decisions associated with it, then you retain that basic structure of the graph, but you change one or two of the probability factors, the CPTs, right? And one of the most common, the first one that was studied was something Pearl called doing, which is just forcing when a certain variable to take a certain value, right, externally. Right. And this fitted in with things like treatment regimes where you force somebody to take a treatment. And then you're trying to work out what will happen to that when you've just observing observational data on these things. Of course, there's loads of assumptions that you're making here. But if you assume that this thing is causal, right, then what you do is you use exactly the same graph, right? The components here are the CPTs. We multiply these together, and we have the same formula associated with multiplying it together because that's linked in with the graph. But we substitute a different CPT for this doing. So instead of having a CPT, if X was a binary variable, for example, setting, instead of having just a general variable, if you set something to take this value xi hat, then you just assign that a probability 1 to put everything else to 0. So you changed the CPT of associated with x1 just to this, right? And then everything else moves forward, xi, and everything else moves forward. So you just substitute that. So that thing, any of the CPTs associated with xi, when we do this, the only things that you change are those things that set xi, that xi has to take a value 1, and then all the other things stay the same, right? So there's a whole technology associated with just doing that, right? But the argument is not necessarily often you find that the Bayes nets that you have of a particular joint is not, the Bayes net is not the natural thing that we should be using for representing a problem. Another thing could be a decision tree, right? Or often in game theory type things, you have event trees and decision trees. So a class of models, the graphical models, which does a Bayes-net type thing to decision trees, is called a chain event graph, right? And this will have exactly the same sort of algebra that can be given to it, which will make things causal. So to say this is causal is you have a graph. This is a directed graph, but it has a different semantic. And it's effectively like a decision tree in the sense that you produce the atoms of the root to leaf paths of this tree, and then you work out the probabilities by just multiplying all the probabilities along the edges of a path, right? And that gives you a joint distribution across the whole of the possible outcomes of the tree, right? And you can make this causal in a very natural way, because what you say here is if this underlying tree represents how things are happening and you want to force something, you just give it probability 1 to a particular edge and 0s to others. And that gives you some sort of causal representation. So if you believe that this is a driving force, so that if you intervene on it, drive model of a process, so that if you intervene in the system somewhere, that effectively the way everything knocks on is represented by this graph, right? Then this will be an appropriate algebra. So I'm assuming that you've elicited things so that they're causal in this sort of way, and that there's a family of causal graphs that's associated with this. Now, I can, as an aside, say that the causal graphs that we've worked with at the moment are very complex. And because they have several different features in them, and I can't talk about that in the space of well, I've only got another 10 minutes, haven't I? So a short period of time. But what I will do is I'll show how this works, and I'll also show you how I can beginning to embed these adversarial atmosphere things. So here's the model I'm going to look at, right? You've got a defender who suspects A is trying to get somebody to infiltrate a particular country by one of 3 ports, and D believes that the probabilities are Q1, Q2, Q2, and Q3, right? And then if they get to the port, there's a probability of PI getting into port BI of being detected for D being able to detect this person who's trying to get into this country, right? You might see that this might be an analog for other types of things, very simple analog, right? So the issue is here, D wants to consider whether it's going to be worthwhile to strengthen their defenses of port B1, right? So that they're sure that they'll catch anybody if they try and get through that port, right? So you can represent this problem with a chain event graph, and look at this problem as sort of adversarial risk within this graphical framework, right? So let's suppose that the defender is just trying to maximize their probability. Their utility function is an indicator on whether or not the agent is detected, so they're maximizing the probability of this person being detected. Then this sort of development can be shown to be best represented by CG, and here we have a CG. Z here represents whether or not somebody is deciding the agent is going to be sent, and then they go so they're either sent or not sent. So we have these things, and if they're sent, they can go to one of the ports, and then there's 2 possibilities: either the person, the agent, is caught, or they're not caught as they go through these things. So essentially, you have a graph like this, and then you have edge probabilities that you would add to this sort of thing, and then the graph represents the problem. So first of all, let's think we've got this is what I would call an inanimate algebra, one where you don't have any reactions from people. How does this work? Well, you've just got to put the probabilities on the edges, which are these things, and you look at it when you make various decisions or not other decisions, and you can then work out the probability of whether or not you're going to catch this person, and they're just given by these probabilities here. So what happens in this sort of setting is that when we look at the particular decision we've got, which is to strengthen B1's defenses, we're just changing the probabilities of the unaffected things to something that is 1 and 0. You're going to definitely catch the person. So when you calculate the expected utilities, obviously that is helpful. Yet you find that you've got something that's always going to be positive because you've just increased a p to 1, an ordinary p to 1. So you gain always. And so when you're looking at these sorts of situations where you just do something and the person can't learn, the adversary can't learn about it, then these sorts of simple algebras allow you to calculate what might be happening and therefore work out how good something is compared to something else, right? But the issue is here, what happens if A learns about this thing? They'll surely try and avoid entering this port if they know that their agent is definitely going to get caught, right, when they're doing that, right? So we need to build in some of this adversarial stuff, right? And fortunately, there's loads of stuff in the literature that tells us how we should be thinking about that from adversarial risk analysis, right? And what we can do is we can use the same sort of idea of using a graph and putting different probabilities on it. The fact is the graph now needs to be embellished so it has nodes that represent things that are associated with the rationality of the opponent, right? So this is a slight aside. Why am I using our technologies? Well, the nice thing about this is that the big thing about these ARA technologies is that they look at the defender, and they look at the game theory problem associated with defending something from the perspective of the defender. And so it's very asymmetric in that way. They're looking at it as not as a joint decision problem like you do mostly with game theory, but as a decision problem that helps one person whilst trying to build in the rationality of somebody else. So we get what the ARA does is get the defender puts themselves in what they think is the adversary's shoes, and they make various assumptions. They assume that they're rational. And if they're rational in a certain way and they've got this graph, you can sort of see, D may not be able to know all the probabilities associated with the thing, but they can begin to see the processes with which that person is going to be reasoning, right? And so we begin to be able to predict the adversary's actions. And we bunged in this parsimony assumption as well, which just says that it's just an assumption that the adversary will not just try and make things more dependent than they need to be. You know, the basic idea being that you randomize as much as what you can do as a good opponent will tend to do that, so that they're only systematic in terms of their decision making insofar as they need to be, right? So that's an extra assumption that you need. But if you build that in, then if you build in the intent capability of knowledge of this other person, right, and you assume that when you do that, that's common knowledge between the two people, then you can start making a move. So what do you do? Well, you go through this process saying that the adversary is going to got this graph, and then they're going to put their probabilities in it, and then they're going to be maximizing their expected utility, right? You then guess what their utility is going to be, and then this gives you a way of actually systematically working out what their reactions might be, and what's going on. Now, obviously, this is highly dependent on the problem that you've got on the graph that you're using to represent it, right? So let me just demonstrate how this works on the example that I just got, right? So let's suppose that we're in that thing, and the agent hears about the fact that the defenses of the first port have been strengthened, right? And let's suppose that we believe that they're just trying to maximize the probability of getting their agent into this system. So that's their utility function, right? Right. And we will also assume that just because they've heard about the strengthening on that port, that doesn't change their beliefs. That won't change their beliefs about what's happening in the other ports. So we can now start to predict this stuff in terms of what will happen, and I'll show you how this sort of unfolds, right? So for this thing, we need another knowledge, a node which represents whether or not the adversary hears about this, right? The utility tells you how much the knowledge impacts on A, right? And what you have here is a capability thing which is associated with, well, if they're going to be trying to move across the different ports, how easy is it for this agent to be able to cross over to different ports and things like that? So this is a new thing. I have a big problem here because all my diagrams have to be planar graphs. Because I don't use a drawing package, I use a matrix package. And so I've missed two edges right here. There's one edge from H to B2, and then there's another one from J to B2. So it's that there should be an arrow there and from the arrow there. But this represents the new graph, the new CG associated with what I've just described. Right? And so again, we just go through the same process. We bring these probabilities in. And if we work out the sorts of root to leaf paths associated with the various outcomes, then we end up with making these probabilities are going to be the same if you don't do anything, right? But the probability associated with this strengthening the defenses on this port becomes this function here of these processes, right? And the interesting thing here is what we're bringing in here are two new probabilities, the probabilities of actually managing to get from port 1 to port 2, or port 1 to point 3, the agent being able to do that. The defender has to sort of work out what that might be, and then they can calculate whatever's going on. All the other stuff is as it was, right? So how do you do that? Well, you can we can just sort of bring this in, because we can say, well, if this is the graph associated with the defender, it's also associated with the adversary, and therefore we have the same formula that comes out of this thing. Right? And these are the decisions that the adversary is going to be making. The only thing that can obviously affect is where they move the agent to, which is associated with this term, right? And you can start thinking about that, right? This they're going to try, and if I'm maximizing this function, I just have to maximize this function, right? So how am I going to fit these things in? Well, these stars are what the adversary thinks. They're giving the probabilities to. The probability, if they're an intelligent adversary and they've seen the same results the defender has, a default assumption is to assume that these things are going to be the same, and therefore the probability that D decides this Q1 star and Q1 3 star, those probabilities of them moving to one thing or the other is determined by how big, whether or not P2 star or P3 star is bigger relative to how easy it is to happening. So just by thinking about this issue, right, we can actually use that to plug in these values of whether or not somebody chooses something, right? And this gives you a new formula. Now, there are various things to pick out. First of all, this is a little bit more difficult, but we are talking about by actually looking at this systematically, it forces you to think about various small bits of the problem rather than the whole bit of the problem to work out what the efficacy is. Secondly, what you can see here is that this function, if you look at this function carefully, it isn't always best to do something. And why is this? Well, what might be happening is if you strengthen defenses on B1, this may force them to move. And if they can move easily to another place where the agent is less likely to be detected, right, then you've actually by strengthening the thing there, and people knowing about it, you've made things worse for yourself as a defender. That sort of process has actually just the working in this way. That sort of outcome just comes out of just the algebra, right? So there are various, so that's all too much probably. Anyway, there are many. That's just a simple example to describe how this sort of stuff is going on. But one thing that we're doing at the moment is producing these graphs that are associated with various sorts of causal processes seen in various adversarial settings. And these things include bot attacks. We've done a close analysis of the Trump-Clinton election things. We're looking at loads of terrorist stuff, exfiltration plots and that sort of stuff with various agencies, right? We have Python code that actually does this, right, for certain things that we've delivered to our friends in high places. And the actual structural elicitation of these things, producing these bespoke graphs, have now been completed for many threats, right? And are currently being tested. Of course, there's extra problems associated with this thing. You can get a lot of the structural information that's open source about how certain crimes happen and certain outrages happen. Getting data and getting expert judgments about what different people do is highly sensitive. So a lot of the elicitation needs to be done remotely associated with this sort of stuff. So a lot of the elicitation is to train other people to do in-house elicitation for various necessary things, and then hold their hand when you go through this process. But we have new ways of dealing with that issue, and in a paper I'm preparing for Tina's special issue, we will be writing about that later on. So this is a headline. These graphs, these bespoke graphs, are very useful in terms of studying defensive measures. And if you combine them with trying to produce not only graphs of what's actually going on, but causal graphs of processes, which are invariant to various basic decisions associated with things, they give you an insight into what the adversary will be thinking as well, right? So the more descriptive and the more realism that you build into the system about the process, the more helpful they are. The thing is from this. So this isn't just like looking at the data and fitting a Bayes net or something. It's about eliciting a Bayes net which represents the processes, and then checking to see whether or not that the data is consistent with that Bayes net. Right. Anyway, once you've done this process, you can produce these things I call intelligent causal algebras, which allow you to populate your probabilities that you need for expected utility stuff. And with ARA technologies, these really do enable you to combine expert judgment and data in a systematic and justifiable way for decision support. So that is what I've been doing. I'm sorry I went on, as I always have done, and thank you so much for your patience, and particularly Roger, who I love to watch when he always looks as if he's listening. You know, it's a wonderful skill, and thank you, Roger, for watching me while I've been doing this presentation. Thank you. Anyway, bye-bye.